Okay, so we're going to whiz through trig really quickly. And then tomorrow we'll get into functions and finish trig and getting into functions. I will do all my lectures by hand. I think it's way better for students, especially online. A lot of people try to use slides, and slides are a bad way to do math, really a bad way to learn math. I think it's always too fast. So I like to handwrite my lectures, basically how we would see it if I were lecturing in person. So we want to go over Appendix A, which is going to be all of trig, which we want to do in 2 lectures. And we've only got a few minutes left today, about 20 minutes. So we're going to go through pretty quickly. First thing we want to cover is, what is a radian? And why do we measure things in radians? So what is a radian? A radian, if we are given an angle, so what is an angle? An angle is drawn by 2 rays. So if we have 2 rays with a common vertex, we create an angle. And what is a radian? Well, for any circle that is drawn with the center at that same vertex of the angles, we can look at the ratio of the radius and the arc length. So our arc length S is going to be the arc length of the circle here. And again, it doesn't matter how big the circle is drawn. 1 radian is essentially the arc length of whatever unit. So 1 to 1, where this is going to be the arc length and this is going to be the radius. In other words, it is the ratio between the arc length and the radius. In other words, an angle theta given in radians is going to be S over R. So 1 radian means we have an arc length equal to the radius. So it is in many ways like a geometrically perfect or a geometric way of describing angles. So if we use degrees, the problem with degrees is that, well, we kind of have this arbitrary number of 360. Why do we use 360? We can talk about that. And, there's a lot of different reasons and ideas behind it. But if we change that unit of measurement, the numbers are going to change. Whereas the radian is intrinsically designed, inherent to the angle. And it doesn't matter which size of circle we use. So hopefully everyone knows that.
Sorry,
was there a question?
Yeah.
Guys, please keep yourselves muted if you can. If you have a question, feel free to speak up. Otherwise, please keep yourselves muted if you are talking to anyone else on the phone or anything like that. Okay, so hopefully everyone knows that the circumference is going to be 2 pi r. So of course the circumference is essentially just the arc length of all the way around. And so using that and using our knowledge of degrees, we can convert from radians to degrees, that there are 180 degrees per pi radians. The other thing to note is that radians are technically a unitless number. Since radians are designed by a ratio, we could have used any units we want here that typically measure length. So let's say meters. So if we have a 1 meter arc length relative to a 1 meter radius, then that's going to give us 1 radian. But of course, because we are using a ratio, those units would cancel out. They would essentially be a unitless number. So our radians, we typically don't write the word radian for there and just write it as a unitless number. So I guess one other formula to modify, if we take this formula here, we can solve for our arc length formula, namely that the arc length is going to be given by theta times r. We measure angles in a coordinate system in standard position. So typically with our course with calculus, we are going to be using Cartesian geometry. All the math and all the geometry that we're going to be doing is in the Cartesian plane, our standard XY plane, and our angles are going to be measured from the positive x-axis. So since we need two rays to measure an angle, we typically assume that the initial ray is going to be on the x-axis, and then the terminal ray somewhere in the Cartesian plane, and we measure positive angles counterclockwise going from the positive x-axis. Given an angle, we can define our 6 trig functions. So for any point on the terminal side of the ray, it's going to have some xy coordinates. And based on the xy coordinates, we can find the length of the ray or the distance from the origin to that specific point that we choose on the ray. So this is going to be given by our Pythagorean theorem, which hopefully everyone knows. So r is square root of x squared plus y squared. And then our angle theta, again, measured in standard position, we can define our 6 trig functions. So our 6 trig functions, sine of theta is going to be y over r, cosine theta is going to be x over r, tangent of theta, y over x. And then the reciprocal trig functions, cosecant of theta is r over y, secant of theta, r over x, and cotangent theta, x over y. Do a little geometric spatial reasoning yourself, and it's going to come down to an argument of similar triangles that it actually doesn't matter what point we choose along this terminal ray. So again, this ray extends out to infinity. So if we picked any other point with a different x and y coordinates, we could compute these 6 trig functions. And because of similar triangles, these functions are well defined, meaning that they have one specific value. That even if I change a different point and use different x and y values, because of the fact that we are using ratios, these ratios are going to be the same no matter which point we use. So the way I continue from here in terms of trig, I like to jump into reference triangles. This might be a little bit different from how you guys do it or how you guys have been taught in the past. A lot of people use the unit circle. So on this note of using any point on this terminal ray to define our xy coordinates, it is often the choice that we choose that this point lies on what's called the unit circle, meaning that this r value is just 1. So if the r value is 1, the specific x and y coordinates are going to be less than 1, less than or equal to 1, and then our trig ratios on the unit circle can be defined in terms of only the x and y coordinate or a ratio of those x and y coordinates for tangent. So a lot of people have seen on the unit circle, the sine ratio is just going to be given by the y value, the cosine ratio is just going to be given by the x value, and then all the other trig functions you can essentially define based off of those. I don't like to use that because then students feel the need to memorize the unit circle. You draw the big circle with all the lines, with all the angles, then you have a bunch of ratios listed there. And in my opinion, I find that causes more mistakes than not, or it's easy to memorize. One, it's hard to memorize because there's a lot of information there. And then because it's harder to memorize, it's easy to flip things around and get things a little backwards, and then you make some small mistakes, either flipping sine or cosine or something to that effect. What I would prefer is for everyone to start to master their own sort of geometric and spatial reasoning, as well as sort of deductive logic. I think that's going to carry you a lot farther in your programs. And so on that regard, I would recommend memorizing as little as possible. So in terms of memorizing as little as possible, reference triangles are one of the few things I do prefer to memorize. So it's pretty easy. Hopefully most people have seen something in this regard, where we have two reference triangles, a 45-45-90 triangle and a 30-60-90 triangle. In terms of radians, the angles are going to be pi over 4, pi over 4. And then over here we have pi over 6 and pi over 3 radians. And nicely enough, the ratios of the sides are easy to remember. So in a pi over 4, pi over 4, pi over 2 triangle, the ratios of the sides are going to be 1, 1, square root of 2. And then in terms of a 30-60-90 triangle, or pi over 6, pi over 3, pi over 2 triangle, always remember that the short side is 1. The long side, the longest side of a triangle, of a right triangle, is going to be the hypotenuse, is going to be 2. And then the other side, square root of 3. So careful with that. Make sure you're drawing things to scale. Drawing and visual spatial reasoning in the applied math program is a very important skill. You will use it up through and including Calc 3. So when you draw these triangles, make sure you draw it to scale so that way you know which side is the short side. Always 1. And then, of course, the angle opposite the short side is pi over 6. The hypotenuse is 2. Other side is root 3. 1, 2, square root of 3. Pretty easy to remember. And then from that, we can essentially evaluate these trig functions now on any angle in our Cartesian plane. So the other thing I would like to include, or just point you guys towards, is what I call counting in fractions. Of pi. What does this mean? Well, the concept is actually fairly easy if I write it down. Pi is going to be pi, 2 pi over 2, 3 pi over 3, 4 pi over 4, and 6 pi over 6. Given our reference triangles, so these are angles that we can compute by hand. So anything with a denominator of 3, 6, 4, or 2, or 1, we can evaluate our trig functions on by hand. So generically, this is a pretty easy statement. We can do the same thing with 2 pi. So 2 pi is 4 pi over 2, 6 pi over 3, 8 pi over 4, and 12 pi over 6. So using our reference triangles and using reference angles and this notion of counting in fractions of pi, we can now evaluate the 6 trig functions on any angle in the Cartesian plane. So a few examples. Keep that handy. Sorry, I have to switch sheets here. And let me know if I ever kind of switch pages too fast or if people are still writing. Let me know. I can always bring back the other sheet. And so let's do something like theta is equal to 5 pi over 4. So how do we find 5 pi over 4? The idea is you want to find the angle that it's closest to, either pi or 2 pi. So we measure angles from the positive x-axis. So the positive x-axis is good, but the negative x-axis also isn't bad. So our reference angle always drawn with x-axis. So how do you figure out where 5 pi over 4 is? Well, we look at whichever one it's closest to. So in our counting fractions of pi, 5 pi over 4, the denominator is 4. Which one is it closest to? It's actually closest to 4 pi over 4. So 4 pi over 4 was the negative x-axis. So 4 pi over 4 is halfway around the circle. How do we get to 5 pi over 4? Well, we go 4 pi over 4 and then one more. So this term here tells us that the reference angle we are looking at is a pi over 4 reference angle, and it's just rotated around into this quadrant. We go 4 pi over 4 plus pi over 4 more to get an angle of 5 pi over 4. And once we know that, we know the denominator of this fraction is 4, so it's a pi over 4 reference angle. We know that the triangle is going to be the same as our pi over 4 reference triangle. So all of the side ratios are going to be equivalent to that. So our side ratios are 1, 1, and square root of 2. The only thing we do have to mind now, since we are in a Cartesian coordinate system, is that the x and y coordinates could potentially be negative. So here, since we are on the negative x-axis, the x value is negative. And then we go downward, y value is also negative. And now we can evaluate all the trig functions on this. One thing to note is that the horizontal, or excuse me, the hypotenuse is always positive. This hypotenuse is considered as a distance. So it's always going to be positive no matter where we are in space. And so now if we have to evaluate trig on this angle, I'll do a few of them. I'll let you guys solve for the rest of them. So our sine of theta is going to be the y value of the hypotenuse, or the opposite side over the hypotenuse. So we will have negative 1 over root 2. If we want to do tangent of theta, we're going to have negative 1 opposite side over the adjacent side, or y over x. And so our tangent theta is 1. Likewise, let's do one more. Let's say 11 pi over 6. So again, how do we find 11 pi over 6? We take a look at the denominator. It's a 6. So we're going to go over here in our fractions of pi. How do we find 11? Well, it's closest to 12. So what is 12 pi over 6? Well, 12 pi over 6 is all the way around, is a full 360, a full 2 pi circle, but that's too far. We need to go back one. So 11 pi over 6, we can go all the way around the circle and then just go back a small distance of pi over 6 in terms of our angle. That means if we go all the way around and then backwards, so a negative angle just means we're going around the opposite direction. So we're going around clockwise with negative angle. So this angle here is just going to be a pi over 6 angle. And then our angle all the way here is our 11 pi over 6. Evaluating the trig functions on this now simply amounts to evaluating our trig functions on this reference triangle, which we can now fill in our sides. Short side 1, hypotenuse 2, other side root 3. And then now in our geometric and spatial space and spatial reasoning, we can assign our negative values. So our x value is positive. We are on the positive x, but we go down. So we are on a negative y value. So the y value has to be negative. And so now if we evaluate, say, sine of theta, it's going to be negative 1 over 2. If we evaluate cosine theta, going to be positive square root of 3 over 2. And then you can evaluate the other trig functions, again, based on those ratios. So with that, another handy reference thing in terms of things you may want to memorize, other than our reference triangles, is this chart here. Mnemonic device, all seniors take calculus, or all students take calculus is commonly used. What this tells us is which trig functions are positive in which quadrant. So all the trig functions are positive in quadrant 1. Only sine is positive, and the reciprocal of sine. So sine and cosecant are going to go hand in hand since they are reciprocals of each other. So cosecant is 1 over sine. So sine is going to be positive. Tangent and cosine are negative. Likewise, here, sine and cosine are going to be negative in quadrant 3. This is another way of evaluating the trig functions. Another way we could have done this is we could have said, well, 11 pi over 6, the reference angle, since the denominator is pi over 6, I could do sine of theta. And if I look at this pi over 6 reference angle, sine is 1/2. But once we found the quadrant of 11 pi over 6, we figured out it's in quadrant 4. And so in quadrant 4, we see that cosine is positive, which means sine has to be negative. And so we found our negative sign. Of course, the reason for that negative sign was that negative y value. Question in the chat, do you have to rationalize? In my opinion, no. I don't think, this is my first time teaching Calc 1 in the applied math. In the math department, we don't make you guys rationalize. So like in the denominator, if you have like 1 over root 2, in my opinion, that's just as fine as root 2 over 2. Or if you get a root 3 in the denominator, I think that's fine as well. Any other questions? Okay, so tomorrow we'll continue with this. We want to brush up on solving trig equations. Those can be a little tricky. Maybe briefly touch up on the graphs and some of the trig identities. Most of the trig identities I'm just going to point you towards in the book as references. I don't think most of those you don't really need to memorize. I'll let you guys know which ones I think you should memorize. But I do want to go over briefly solving trig equations. Those are some of the more difficult things that we do in pre-calc, and then they're going to show up throughout calculus, throughout Calc 1, Calc 2, Calc 3. So those skills are really important. Make sure you guys brush up on those. And if you ever want any extra help, feel free, come to office hours, and I will get you caught up with all those and help you practice.